Hi everyone, I'm Rashmi. I'm a PhD student in the ECS department at UC Berkeley. Today I'll talk about erasure coding for distributed storage. In particular, how to jointly optimize for I/O, storage, and network bandwidth. This is a joint work with my collaborators at Berkeley, Preetum, Jingyan, Nihar, and Kannan. As we all know, in distributed storage, data needs to be stored in a redundant fashion in order to ensure that it is durable and available upon request. Simplest approach of introducing redundancy is replication, wherein multiple copies of the data are stored on different machines. An alternative approach that has gained popularity is that of using erasure codes. It is well known that erasure codes are more efficient in utilizing storage space to provide fault tolerance as compared to replication. In fact, traditional erasure codes such as Reed-Solomon are optimal in this respect. That is, they provide the maximum possible fault tolerance for the storage overhead used. When using erasure codes for distributed storage, another important metric needs to be considered, and that is of maintenance cost. Maintenance involves replacing missed or otherwise unavailable data in order to maintain the desired level of reliability, redundancy. So this is a frequent operation in distributed storage systems and is important because it consumes network and I/O costs. Traditional erasure codes turn out to be highly inefficient in this respect. Before jumping in, here is a high-level view of what this talk is about. Traditional erasure codes are highly inefficient in replacing missing or unavailable data, which is a frequent operation and important in distributed storage systems. There has been considerable amount of research in the recent past, both in the theory and systems community, to tackle this problem. A powerful class of erasure coding framework has been proposed which optimizes only for storage and network bandwidth. And in this talk, I'll show how to transform these codes to optimize I/O as well while retaining the optimality with respect to storage and bandwidth. First, let us see why traditional codes are inefficient in replacing missing data. So we'll call this operation as reconstruction. Consider storing 4 data blocks, 1, 2, 3, and 4. And on the left, you can see a 3-replicated system where all the blocks are stored on different machines. I will refer the term block in an abstract sense, and it can map to any data unit in the system, such as a file or chunk of a file. In an erasure-coded system, there are no replicas, and instead it consists of parity blocks. So on the right, you can see an Reed-Solomon coded system, which consists of 3 parity blocks, 5, 6, and 7. And this is a 7-4 Reed-Solomon code, where 4 stands for number of data blocks, and 7 stands for the total number of blocks, which includes the 3 parities. Reed-Solomon code generates these parities, which are carefully designed functions of the data blocks, such that any 4 of these 7 are sufficient to recover the original data. Okay, now when a block fails in the replicated storage system, it can be replaced by just copying it from another replica. So the amount of data that is read and transferred, that is the I/O and network cost, is equal to the amount of data that we are reconstructing. However, in the erasure coded system, there is no such replica. So for these parameters, in this example, we need to obtain any 4 of the remaining 6 blocks and decode the desired block. So the I/O and network cost involved is 4 times the amount of data we want to reconstruct. In general, Reed-Solomon codes, which are the most popular codes employed in practice today, are associated with 2 parameters, k and n. It takes in k data blocks and generates n minus k parity blocks. So in total, we have n blocks. And any k out of these n are sufficient to recover all the original data blocks. And this property provides the optimal storage and fault tolerance that is offered by Reed-Solomon codes. And for reconstruction of any block, we need to obtain any k out of the remaining n minus 1 blocks. So the I/O and network costs involved is k times the amount of data being reconstructed. For typical parameters, this is between 10 to 20x. This is an important problem, and there has been considerable amount of research in the very recent past, both in the theory and systems community, to address this problem. And in this talk, we will deal with one of the solutions, which is minimum storage regenerating codes, or the MSR framework. MSR framework is a theoretical framework that allows for optimizing storage and network bandwidth costs. Using information theory related arguments, it tells us what is the minimum amount that needs to be transferred in order to perform reconstruction. Just like in Reed-Solomon codes, it consists of k data blocks and n minus k parity blocks. And any k out of these n blocks are sufficient to recover all the k data blocks. So this framework is also optimal with respect to storage and fault tolerance, just as in Reed-Solomon. Under MSR framework, any block can be reconstructed by connecting to any d of the remaining n minus 1 blocks and transferring a small amount of data from each. The total amount of data that is transferred from all these helpers is significantly smaller as compared to that in Reed-Solomon, and it is also the minimum possible. Let us see this in an example. Consider 6 data blocks and 6 parity blocks with a block size of 16 megabytes. Under Reed-Solomon, any block, let's say block 1, can be reconstructed by connecting to any 6 of the other blocks. We'll call them as helpers. In this figure, 2 to 7 are the helper blocks. So we can reconstruct block 1 by obtaining these 6 blocks. So the total amount of transfer is 96 megabytes. However, under the MSR framework, with D, that is the number of helpers, as 10, the same reconstruction can be performed by downloading only 3.2 megabytes from 10 of the remaining 11 blocks. So the total transfer involved is only 32 megabytes. While the MSR frameworks allows for optimizing for storage and network bandwidth costs, it does not consider the cost of I/O at the helpers. So let us see this in our example. So let's consider block 2, which is one of the helpers. So helper reads its block of 16 megabytes and computes a function and transfers the resultant, which is of much smaller size, which is 3.2 megabytes. So while the amount of bandwidth consumed is minimal, the amount of I/O consumed is not reduced. In fact, it is higher than in Reed-Solomon because we have more number of helpers. While the Reed-Solomon code had 6 helpers, MSR framework has 10 helpers. In general, the codes under the MSR framework optimize for storage and network bandwidth, but they do not optimize for I/O. And in this work, we consider optimizing for I/O as well, while retaining the optimality with respect to storage and network bandwidth. Okay, in this talk, I'll present 2 algorithms that together transform MSR codes into codes that are efficient with respect to I/O as well, while retaining storage and bandwidth optimality. First algorithm transforms MSR codes so that they are locally I/O optimal at each helper block. And the second algorithm builds on top of the first to minimize I/O cost globally across all the blocks. But before going into the details, I want to show you the kind of performance improvements that can be obtained by applying these transformations. So we'll apply these transformations to a class of practical MSR codes called product-matrix-MSR codes. And let us call the resultant code after transformation as PMRBT. So this nomenclature will be clear when we go into the details of the algorithm. PM codes exist for parameters where the storage overhead is greater than or equal to a value which is slightly less than 2. And for this amount of storage overhead, they provide the maximum amount of fault tolerance possible. These are applicable in applications where, which need high fault tolerance, such as high churn applications like peer-to-peer storage. So we implemented both the original and the transformed codes in C and evaluated it on Amazon EC2 instances. We are using Erasure 2 and JF Complete libraries for the finite field arithmetic and RS. Let us first consider the amount of data transfer during reconstruction. The plot here is for the parameters k, that is number of data block 6, and the number of helpers d being 11. So we can, and the block sizes are 16 megabytes. We can see that both the original and the transformed code, in this figure, PM refers to the original code and RBT refers to the transformed code. Both of these have significantly lesser amount of data transfer, that is network consumed during reconstruction. And we observed similar performance for other block sizes as well. And I want to emphasize that the transformed code retains the bandwidth optimality of the original code. Now let us consider the number of IOPS consumed during reconstruction. So the plot is for the same parameters as before. First of all, we can see that the PM codes require significantly higher IO costs than Reed-Solomon. And the transformed codes result in significant savings in IOPS as compared to both Reed-Solomon and PM codes. In fact, they result in 5x lesser IOPS as compared to PM and 3x lesser IOPS as compared to Reed-Solomon. And we observe similar savings for other block sizes as well. Next, we consider IO completion time. During reconstruction, IO at all the helpers is happening in parallel. So the IO completion time is the maximum of the IO completion times at all the helpers. The plot is again for the same parameters. And we can see that the transformed code results in significantly faster IO because it is doing lesser IO in each of the helpers. And we observe similar savings in other block sizes as well. Okay, now let us see how these transformations can provide this kind of performance improvement. Recall that in the MSR framework, at the helper, the block was read. In our example, it was 16 megabytes. A function was computed, and the resultant, which is of much smaller size, which was 3.2 megabytes, was transferred. So while the bandwidth consumed was minimal, IO consumption was not reduced. We would like it if the helper reads only the amount of data that it transfers. That is, the amount of IO consumed equal to the amount of bandwidth consumed. When a helper helps in this fashion, we will call it as doing reconstruct by transfer. That is, it doesn't do any computation, just reads and transfers. Algorithm 1 transforms MSR codes to achieve reconstruct by transfer at the helpers to the maximum extent possible. And it is applicable to all MSR codes that satisfy two properties. The first property requires that the function computed at a helper is not dependent on who others are helping. So let us take an example. So this is an example consisting of 3 data blocks, and let us say D, that is the number of helpers, is 4. The picture shows reconstruction of block 1 with helpers being blocks 2 to 5, and the data stored in block 2 is denoted by B. So in this case, when 3, 4 and 5 are the other helpers, block 2 transfers the function F1. This property requires that when the other helpers are different, block 2 still transfers F1 in order to reconstruct block 1. So what this means is that when property 1 is satisfied, each block has a predetermined function that it transfers to reconstruct each of the other blocks. So block 2 sends F1 to reconstruct block 1, F3 for block 3, and so on. Property 2 deals with the independence between these functions. it requires that any subset of size equal to the block size being independent. So in this example, where we had number of data blocks as 3 and number of helpers as 4, each of these functions turns out to be half the block size. So when property 2 is satisfied, any two of these functions would be independent. Now the main idea behind algorithm 1 is precompute and store. That is, we just saw that when both properties 1 and 2 are satisfied, the predetermined functions that a block transfers in the reconstruction of other blocks, in our example, was half the block size and any two of them were independent. So algorithm 1 would transform this block to store any two of these functions. So let's say F1 and F3. Now block 2 can reconstruct blocks 1 and 3 in RBT fashion, because when helping block 1, it just reads and transfers the first half of its block, and when helping reconstruct block 3, it reads and transfers the second half. Under MSR, whenever a helper does reconstruct by transfer, it is doing minimum IO. This is because under reconstruct by transfer, amount of data read is equal to the amount of data transferred. And under MSR framework, we know that this is the minimum amount possible. So in our example, block 2 would be doing minimum amount of IO when helping blocks 1 and 3 in reconstruction. For helping reconstruct other blocks, it will have to read the full block and do computation just like in the underlying code. The choice of these functions to be stored, that is in our example F1 and F3, was arbitrary. That the algorithm 1 takes this as an input and then performs the transformation such that for this choice, the block performs reconstruct by transfer. But this could also have been F4 and F5, in which case the block would do minimum IO when helping reconstruct blocks 4 and 5. So how do we choose this assignment of which blocks help which other blocks through reconstruct by transfer? Algorithm 2 deals with this question, and it chooses this RBT helper assignment in order to minimize the IO cost globally across all the blocks. So I'll not have time to go into the details. It is available in the paper, but I'll just mention that this algorithm is a greedy algorithm, and in fact, it is optimal for this assignment problem. I'll mention two extreme cases of this algorithm. The first one is which gives complete preferential treatment for the data blocks. That is, all the blocks help all the data blocks to the maximum extent possible, and we will refer to this helper assignment pattern as SYS. The second extreme case is which gives equal treatment for all the blocks, in which case it is optimal when each block helps the following blocks in RBT fashion in a cyclic pattern, and we will name this kind of helper assignment as CYC. Now let us look at the impact of these transformations on the encoding and decoding speed in the same evaluation that we saw. First is decoding speed, that is the speed of computation performed during reconstruction operations. The plot shows decoding speed for varying values of k. We consider n is equal to 2k, that is there are k parities, and the number of helpers d is 2k minus 1. All of these are single threaded. So first of all, observe that the transformation does not affect the decoding speed. Both the original and the transformed code have the same decoding speed, and these are the purple and the blue lines at the center which are almost overlapping. The other three curves in the plot are for Reed-Solomon, and the first curve, which is at the top in red, is our Reed-Solomon decoding connecting to all the remaining data blocks and only one parity block, which is very fast. And the second curve is Reed-Solomon decoding using 2 parity blocks and other data blocks. And the bottommost curve is Reed-Solomon decoding using all parity blocks. So we can see that the decoding speed in both PM and PMRBT are close to Reed-Solomon decoding using 2 parity blocks. This plot presents the encoding speed, that is speed of generating the parities. So the top curve in red is the Reed-Solomon, and the remaining 3 curves are for the original product matrix code and the transformed codes for 2 extreme cases of helper assignment problem that I mentioned. So first of all, we see that encoding speed of both the underlying code and the transformed code is slower than Reed-Solomon, but it is still practical. One interesting point to note here is that the sys helper assignment pattern, that is in which the data blocks gained complete priority, wherein all the blocks would help as many as possible data blocks in doing reconstruct by transfer, is significantly faster as compared to the underlying code also. So this is because this transformation makes the encoding matrix sparse, which makes the encoding speed faster. In summary, we present algorithms to transform MSR codes to optimize I/O as well while retaining storage and bandwidth optimality. We implemented and evaluated this by applying it onto a practical class of MSR codes, the product-matrix-MSR codes. And in the paper, we also have analytical results showing optimality. Thank you, and I'll be happy to answer any questions.
Yeah, excellent work. Quick question. I was curious about how the compute bandwidth was traded off, because you have more helpers, so your code construction, I'm assuming you're doing it in software, so you're able to retain the speeds, but the equations have gone bigger. So I think in your AWS model, I think that trade-off was, I mean, maybe it's in the paper, so I apologize, I haven't read the paper.
Thank you. Yeah, so as we saw, there is a compute trade-off in terms of this resource utilization optimization. And, but we see that it is still practical enough. So for example, the compute cost during decoding was similar to decoding using 2 parities in Reed-Solomon. So the compute cost is actually not too high because the amount of data that it churns is much lesser as compared to that in Reed-Solomon.
Hey, I'm Keith Smith from NetApp. I thought it was really cool. The examples and stuff you used in the presentation all basically just used one erasure, so I'm wondering what the efficiency of this works out to be when you've got multiple erasures, because if you're doing, you know, K and N with large numbers, you presumably want to be able to handle that.
Yeah, that's a good question. Currently, the MSR framework considers optimizing only for one failure, but it requires D helpers, and any D are sufficient out of the remaining N-1. So there is room for considering multiple failures in that respect. But it is up to the amount of extra nodes that you have over the chosen parameter D. But typically, in some applications, maybe like data centers, one failure is more common than multiple failures. Thanks.
I think we can take one quick question.
Yeah, very interesting talk. Just wonder, in algorithm 1, do you change the layout of both data and parity blocks?
No, there will be no change in the layout. But this is a good question because I didn't get the time. But it seemed that now all the data blocks have transformed and they have become like parity blocks, right? But this is not true, and I have a backup slide on that. So basically, what can be done is that the original K data blocks can be remapped by doing the transformation before doing the encoding, such that the resultant code becomes in what is called systematic form. That is, you'll still be retaining the data blocks and parity blocks form, and only the functions in the parity blocks would be changed.
Okay, thanks.
Thank you.